So today we're going to talk about NVIDIA developer tools. So we're going to focus mostly on the profiling tools and talking about performance. We actually have a handful of other tools we're going to talk about for correctness as well. But right, you're all here for exascale and HPC and some idea of getting better performance. And certainly if you drop a GPU in there as an accelerator, right, your goal is to accelerate things and get even more performance. So performance is very, very critical, and being able to kind of manage and watch it as we go along and make changes to our code. So has anyone here done any development and got really into the nitty and gritty of GPU profiling tools? Any like Nsight users? Okay, we got a few around here. Okay, yeah. So right, broadly, things have changed over the last couple of years. So it's even if you have used them before, it's good to get a quick refresh, right? So in the past, we had the NVVP, NVIDIA Visual Profiler, and NVProf, and a couple of years back, we actually went and refactored some of these tools, and we have basically kind of move some things around, and we now have a set of two profilers called Nsight Systems and Nsight Compute, okay? And we're going to talk a little bit about what the difference between those two things are. Very high level Nsight Systems is for a higher level system view, seeing what the CPU is doing, what the GPU is doing, any data movement, where Nsight Compute is more for drilling right into a GPU kernel, looking at register usage, low level memory subsystems, and getting a really detailed look, right? So we'll talk about the profiling tools, and then in the other side, we'll just kind of flash a little bit. We do have, it is developer tools, not just profiling tools. We have debuggers, right? If you're familiar with GDB, which is one of my favorite debuggers, we have CUDA GDB, which has a nearly identical API, and you can, step through CUDA functions. Good integration with we have any Visual Studio users. I imagine in this room we have a lot of probably Vim and Emacs users, and that's what I use. And then, correctness checker. So if you're used to val grind or cache grind, any of those more static analysis tools, look at, out of access or out of bounds memory accesses and whatnot. We have a whole tool suite for that as well, right? All right, so in order to kind of talk about the tools in more detail, let's talk about what we're actually targeting, right? So I know a lot of you folks over the last couple of weeks here have learned about a lot of new programming models, or at least dived a little bit deeper. I remember in 2015 there was a really great OpenMP talk. I think I saw that at the agenda this time, OpenACC, right? All of these things at the end of the day are generating something that we can look at with an NVIDIA profiler. And it turns out that until you get really into the weeds, all of them are almost on equal standing, right? Whether you're on the right here and you're generating very platform-specific code. If you're writing CUDA, right, you're marking up functions, you're orchestrating all the threads, all the thread blocks, you're controlling how memory copies to and from the GPU, you're controlling the kernel launch parameters. Of course, you would expect the profiling tools work for you, right? And they do, right? But what might be more surprising is if you're doing OpenACC, OpenMP, or even more recently, if you're doing accelerated standard language parallelism, right? That means using like std_par in C++ 17, do concurrent in later versions of Fortran, or if you consider NumPy standard Python, which it isn't quite, right? If you're doing like CuPy or any NumPy operations, you can accelerate all of those on the NVIDIA GPU as well, right? And in the case of C++ and Fortran, it's implicit, right? You use the NVIDIA compilers, and it's off to the races. All of these things can be profiled and debugged on more or less equal standing with our profiling tools. Okay, and then finally, in terms of where to get these profiling tools, well, the good thing is they're already installed on a lot of systems you folks have access to, right? Certainly on Polaris. We kind of ship everything together that you need to both write, profile, and debug code in something called the NVIDIA HPC SDK, right? This is maybe about 2 years ago that we announced it. If you can tell from all these blocks, there's probably some familiar faces if you've done GPU programming, but this will include, of course, your compilers. We actually ship an OpenMPI implementation in there that's CUDA aware and has all the UCX patches just right. All the math libraries, the profilers, the debuggers. This is available via direct download on that HPC SDK URL up there. There's tarballs and whatnot. It's on NGC if you're set up to use containers. We have Singularity, SPAC available in the cloud. So, it's just nice because it's one spot. You download this. All the software in here is free. Gets updated 7 or 8 times a year. And if you keep this one package updated, you're going to have all the newest bits of software. All right, so let's get into the profilers now. So, Nsight. So I heard we had a few people who were doing some programming. Probably if you've done it in the last couple of years with the GPU, you took a look at these Nsight tools. As I mentioned, we've kind of split the tools into really 2 tools. There's technically 3 here, right? So on the bottom right, you see we have Nsight Graphics, which is more for graphics, right? NVIDIA does a lot of graphics, believe it or not, right? Between video game engines and Pixar movies and all that, right? Looking at breaking down the frames and getting better performance. But for us folks in HPC doing traditional simulation and AI or ML, we stick with these other two, Insight Systems and Insight Compute, right? So again, let's start with Insight Systems. That's going to give us a really high-level view of our application. We're going to see a timeline. It's going to show us what, if the CPU is running, if the GPU is running, what the utilization is. It'll show us on the timeline if we're transferring data from the CPU to the GPU or vice versa. It'll show if we try to launch some kernel asynchronously and then there's a big gap of time before it actually executes, right? It'll show us that really high level information. And for myself as a solution architect, I'm out there working with developers in higher education. This is the tool that I spend 95% of my time with, right? Because that's where most of the optimizations lay, right? Finding out where the hot spots, where the cool spots are. And then once you have an idea, you have a really good, good idea of what your application is, where you need to spend more time. That's when you break out Insight Compute. I warn, do not break out Insight Compute unless you need, or until you have to, I should say, because it is extremely detailed, very low level information, right? Getting all of the benefit out of Insight Compute requires a very comprehensive understanding of the GPU architecture, how it works, the underlying CUDA programming model. That being said, we're going to show some things that the Insight Compute has, which make it pretty easy to get a reasonable idea of where performance lies. If you're compute or memory bound, right, it has roofline plots and whatnot, right? But the idea is you spend some time in Insight Compute, you optimize it, get it running way, way faster. Now all of a sudden in your timeline, that kernel that used to be a hotspot is half as big because you made it run way faster. So now you have to go back to Insight Systems. Your timeline has changed. Are there new hotspots? Are there new optimization opportunities? Right, so we're going to, as we're talking about profilers today, I'm sure across all of us we're going to hear the word iterative a lot, right? It's always an iterative process. All right, so a little bit deeper dive into both of these two main tools, right? So again, Insight Systems. I know on the right there we see really a pixelated timeline. We're going to zoom in a little bit here on the next couple of slides, but it gives an idea, right? You can kind of see a bunch of bars on the top of things happening, right? Again, high-level application tuning. Cannot stress enough, this is not just GPU. It's also going to show CPU, right, what all the threads are doing, their interactions with the CUDA API, launching kernels, any interactions with the OS and whatnot, and really, this is the tool for finding where you need to spend your optimization efforts, right? Finding where those targets are, where those hotspots are, where those big gaps in the timeline are, where maybe the CPU is doing something and the GPU is just kind of sitting there, consuming power there. And then by seeing a timeline with both the CPU and the GPU, again, without that super deep dive detailed information, you're going to get an idea of what the balance is between your CPU and the GPU. Are they both staying busy, right? If the CPU is idle and the GPU is staying really busy, maybe you can use that CPU and prefetch data and use it to improve my overall performance. Cannot stress enough, right? You can do a lot of work without getting into the weeds there, right? Both of these tools, Insight Systems and Insight Compute, have both a GUI or graphic user interface variant and a command line variant, right? So the idea is if you're on a workstation, right, if you are developing on your laptop or somewhere where you have like local root access, I would say, maybe you like using the graphical user interface. That's available in Linux and Windows, right? You can kind of launch in, it looks like the right. You can kind of click through a wizard. What kind of analyses do I want to look at, right? What level of analysis do I want to do? Hit the start button and it runs the kernel and it spits out a report and you're off to the races, right? But as it turns out, a lot of times for us folks in HPC, right, we don't have X forwarding on the system, or we only have the command line, or maybe we're trying to profile a bunch of threads and there's no way we're going to be able to attach this X window to all of them. So for the command line version, basically you can run this command line variant, right? It will spit out a report, which then you download to your local machine, whether that's like a Mac laptop, your Linux, whatever, and then you can open up the report on your own system and do your analysis, right? So it's much lighter weight. And as it turns out, I was talking with the Argonne folks earlier last week, and for the Polaris system, that's the way to use Insight, right? The command line, get the report, download it to your local system, and for this hands-on session later this morning, we'll actually be connecting to an NVIDIA resource that does have X forwarding, so you can get a feeling with both sides there. Okay, so this is a little bit more zoomed in, right? Still pixelated, just look at the big boxes, right? Any of these profiling tools, you need to spend time with them, right? There's so much information there because you need a lot of information to make, informed choices, informed optimizations. In general, on the top, you're going to get a bunch of CPU information, right? What the processes and threads are doing, any thread or core migration, the thread state, right? If you're using multiple OpenMP threads and whatnot. You're also, as I said, going to see a trace of any of the CUDA API calls. That includes a large number of the CUDA libraries. In this case, this is a Python deep neural network training, so it's going to be calling cuBLAS, which is our BLAS library, or cuDNN for deep neural network convolutions and whatnot. And then, as I mentioned, beyond just the compute, it's going to show you any of those on the CPU side. On the GPU, it's going to tell you both the GPU utilization with respect to how many cores you're using, how many SMs you're firing up, but it's also going to show it with respect to memory utilization, right? So memory bandwidth. And as it turns out, a GPU, you always think of tens of thousands of threads, massively parallel system, and that's true. They are a massively parallel compute powerhouse. But on the other hand, the memory bandwidth is not shabby at all either, right? If you have a memory bandwidth bound operation, like look at the performance of a GPU for FFTs and whatnot, they really scream. So generally you want to make sure you're utilizing both the cores and the memory subsystem. And then finally, this works for multi-GPU. So one of the first things that I usually do when I load in one of these reports is I start collapsing a lot of things because, again, it's kind of information overload. But there on the bottom, you can see if we wanted to open these up, this is running on an 8-way P100 system. So right, you can look at multi-GPU. And even in newer versions of Nsight systems, if you're running like multiple reports with MPI, you can actually merge them and have a single report on the screen, right? So it's a little bit easier to use. Okay, one thing to keep in mind is when you see these utilization bars on this timeline, it kind of looks like a spectrogram, right? If you're zoomed out, what look like these little valleys are, in fact, if you zoom in even closer, gaps, right? Because as you zoom out, this utilization is averaged over time, right? So if it's 25% on that top chart there, that means that over a time period, that GPU was likely sitting idle for 75% of the time, right? And when we're talking about GPUs, really this latency regime and HPC, where performance critical, a lot of times we have to zoom in at that level, and actually those are the gaps that we're really addressing, right? And in general, right, information overload, when we see that spectrogram, it can be tough at times. Anyone who's used any of these profiling tools, for me in quantum chemistry, we have a lot of iterative algorithms where even a small benchmark run may run 30 iterations of an algorithm. And trying to tune in on this big spectrogram, okay, where does the iteration start? And where's the gap between each of those? Can be pretty tough, right? So certainly you kind of need to zoom in and start to look at the different API calls, how long the kernel is running. But to kind of assist with annotating things and actually figuring out where you are in your Nsight tool, we have something called NVTX. Has anyone used this before, NVTX? Okay, yeah. So most of the folks that have used Nsight have probably tried this before. So NVTX essentially allows you to instrument your code or set section of codes and give them a label, right? Maybe instead of having to figure out where I am in this iterative procedure, where this loop is that I think is a hotspot, I can add some NVTX annotations around the do loop, right? And then in my Nsight tool, I'll simply see, right, this range which corresponds to that algorithm taking place in the code, right? So it's a way to basically correlate what's happening in the profile to the actual lines of code there. So very, very important, and this is one of the first things I do to instrument any important code. This this works for certainly for any CUDA C++. Even if you're doing Python and you're doing, for example, CuPy, there's bindings for this, so it's very, very useful there. Another thing that I should point out is while I said you don't get a ton of detailed information about what's happening in the kernel itself and that kind of correlation to individual GPU kernels in Nsight systems, you do get a little bit of GPU metric sampling, right? So if anyone's ever, by any chance, used NVIDIA SMI and really got in the weeds with that, maybe used DCGM, or Data Center GPU Manager, that can take a lot of metric samples. That's what this is basically doing. But it's going to report things, right, like how active your SMs are, right? How much PCI bandwidth you're using, and it's even going to tell you about like point-to-point communication if you have like an InfiniBand adapter in there. So, right, it's not super detailed, but it can give you some more generic information about your application, right? So a few of those sampling metrics that you might want to look at to interpret. First of all, the GR activity, right? Is the GPU doing work? Are the cores actually computing something? And that can mean SMs, which are like the equivalent to a CPU core, but it could also mean things like an NV encoder, an NV decoder if you're doing some graphics work as well. Right? SM activity, SMs are more like the more traditional cores, more apples to apples with the CPU core, right? Are we actually utilizing the width of the GPU, right? And for anyone who's spent time writing CUDA, you have to spend a lot of time manipulating your threads per block and your batch size and whatnot, so we can manipulate that to control our SM activity. Another one you'll often take a look at is the SM instructions issued, right? So this means is the GPU actually issuing a lot of instructions, okay? And if it's not, it means that you might be stalled waiting on memory, right? Maybe you don't have enough warps to cover your memory latency. So there's a number of different ways we can address this. Again, this is all information that we're deriving without knowing any detailed information about the kernel with Nsight Compute, right? Another one is tensor activity. So tensor cores are a special hardware feature on some of the later generations of NVIDIA GPUs that essentially allow you to do matrix multiplications very, very quickly, right? Very useful for machine learning, useful for, in quantum chemistry, coupled cluster, many-body algorithms, right? A lot of folks want to make sure they're utilizing those tensor cores. That's reported on Nsight systems as well. Okay, and then in terms of profiling an application, again, so this is at the command line, right way to do it. So this is something you can throw on a batch system, on Polaris, whatever, right? Pretty straightforward. This is kind of a generic recipe for you. NSYS profile, report, stats equals true. Kind of gives you a nice baseline of statistics that most are interested in. The generated file, depending on which version of Nsight, we recently moved from QD-rep over to NSYS report. But you should get that report file. That's what you're going to want to FTP over to your local machine or wherever you're going to run your Nsight systems graphical user interface. And I should also make it really, really clear. Wherever you run your graphic interface to actually analyze your report, that system doesn't even need an NVIDIA GPU, right? You can run it on a Mac, whatever. It all works, right? And then finally, of course, for HPC, we're doing MPI and we're using Slurm. Generally, I recommend to put the NSYS after the MPI run command. And what that is going to do is actually generate a separate NSYS profile report for each rank. All right, so NSYS understands environmental variables and whatnot on the command line. So if you can even tag up your report name with the MPI rank or the Slurm job or rank ID, right? So, but that's generally the preferred way to do it in an MPI environment. Okay. Do we have anyone here doing a lot of PyTorch, TensorFlow? A lot, yeah. So maybe folks that are using GPUs, but maybe not having to think about it too much, right? A TensorFlow and PyTorch, they've done a very nice job of optimizing everything at an extreme level. But from the perspective of a user, it's a lot of just flipping a switch, right? You're using the GPU-backed version, and it's running faster. I do just want to mention in passing, if you are using these NVTX that I talked about earlier are still very, very important. For PyTorch, they're disabled by default, so there's this little NVTX range that you need to add, and then likewise for TensorFlow, they actually are annotated by default in the NVIDIA NGC containers, but kind of a little gotcha for performance. If you're deploying into production on those TensorFlow containers, you actually want to disable those NVTX ranges, so we have an environmental variable for that as well. All right, some really generic questions these are pretty obvious, but let's just look at it, right? Questions to guide your profile analysis. What are the two questions you want to ask? First of all, what is hot, right? What is taking the most time? What is really getting that GPU screaming, right? And sometimes that's what you want to focus your optimization on, right? Sometimes you're maybe calling an optimized library and there's not much you can really do there, right? So it's not always, but it's often something to spend time on. Can I make it a little bit faster? Can I shrink the problem? Can I maybe get more parallelism out of this? Can I maybe even reduce precision, right? And then another big one, especially in an environment where we're using a CPU and a GPU together, asynchronously, is what's cold, right? Again, I keep mentioning, what are the gaps? When's the CPU doing a lot of work and the GPU sitting there, or vice versa, right? If we have, can we fill the gaps in the timeline, right? Do we have some unnecessary syncs? And again, an optimization that I keep mentioning is maybe can we prefetch on the CPU if we need to keep feeding the GPU with work? Okay, 10 really quick general optimization tips, and we're actually going to apply some of these in the hands-on session later this morning, right? Something you can think of when you're doing GPU programming, right? First, are you using tensor cores, right? Are we using the tensor cores? Can I maybe refactor my problem such that I'm doing a matrix multiplication, right? We see that in a lot of fields nowadays. Am I making sure to minimize any transposes or conversions necessary to do to utilize those tensor cores, right? Another thing is a GPU is most successful when you have tens or hundreds of thousands of cores, many work tasks in flight, right? So can I increase the grid or maybe even the batch size in the case of a deep learning workflow to utilize the GPU a bit better, right? Of course, conventional parallelism, right? Easier said than done, but right with GPUs we want to do more work. In some cases, you look at algorithms and codes that were written decades ago where maybe memory was a bit more expensive and they wanted to, maybe avoid recomputation and whatnot, right? We can start kind of revisiting some of those things. And then if you're doing, if you don't have any data dependencies in your algorithm, maybe you can reorder things and get some pipeline parallelism, right? Another big one that I see very, very often, especially in initial ports from a CPU to a GPU code, is when you're submitting a lot of really, really tiny kernels to the GPU, really small little pieces of work, right? What you have to keep in mind is each time you're submitting a job to the GPU or some kernel of work, there's going to be some latency and some overhead associated with that, right? There's the CUDA API, the OS interrupt, the GPU might be working on something else that it has to move over. So, right, if you're doing a bunch of small operations, consider fusing them together, right? Fusing, although it may seem counterintuitive to what we want to make functions small so the compiler can do good work on them, right? In this case, it's very often you want to combine work together and reduce the number of kernel launches you have, right? MPS, has anyone here heard of MPS before? Okay, MPS, I hope more folks check this one out, especially if anyone's doing molecular dynamics simulations or running any applications that have very irregular workloads. MPS basically allows you to overlap or oversubscribe the GPU and submit multiple jobs at the same time. Okay, so in a lot of cases, if you have something that's hitting on one side of the GPU really hard, and then for the next part of the job it's hitting over here, right? You can overlap another job such that it's balancing out. In some cases, there's actually a blog post for GROMACS simulations where we saw better throughput on the A100 when we stacked 27 jobs on top of each other running at the same time, right? So definitely something to check out. Multi-buffering, right? If we have maybe multiple threads that are kind of fighting over the same piece of data, maybe we can double or triple buffer and store multiple copies of that data such that they're not fighting each other. A big one, avoid moving data to and back from the CPU, right? If you don't move something back to the CPU unless you need to, right? Keep intermediates on the GPU. And then, of course, if anyone's using managed memory before, that's a really nice programming convenience feature, which basically lets you treat the CPU and GPU memory space as a single address space. Big problem with that is page fault, so make sure you're prefetching memory at any given opportunity there. All right, and then finally, the really nice thing for Nsight systems is recently they added kind of this wizard here, which I really love this with all the profiling tools. We need more of it. Just gives you kind of plain text recommendations, right? You ran your profile through there. It at least gives you an idea of where to look at. In this case, they were trying or in this case, they were allocating something in pageable memory instead of pinned memory, right? Right, they're making that recommendation so they can use async memcopy. Really, really good just to have plain text, right? So the next thing, right, so there's already a lot of information on Nsight systems we saw, but I want to talk quickly about Nsight compute, right? This is the one, again, that's going to allow us to dive in at a really, really deep level. You can see there on the right, all of these different instructions, how many times they're executed. Down there at the bottom, you can kind of see this assembly stuff, right? Things that I hope to need to get into unless I really have to, right? Or ask somebody to help me. But that being said, right, this is really for that expert level view. And same case here, right? We have the command line and the GUI variant there. Okay, there's a ton in here. One thing that I'm going to mention right away is you can barely see it, but in the top right here, there's a little plus sign. One of the first things you should do when you open these reports is hit that plus sign because it actually opens up a lot of really useful visual diagrams that I think are useful even on first pass. Right, the top one here is this GPU speed of light. It's going to tell you things like your SM utilization, your memory utilization, how you're utilizing each level of the cache, right? Not too deep yet, I would say. But generally, these are bars that you want to get high, right? You want to have the SM and memory utilization. If you're somewhere around 60 or 70% on both of them, you're generally doing pretty good, right? And there you go, again, that kind of built-in expertise, right? That plain English, hey, this looks like a bottleneck. You should try flipping this, try tuning this up, try putting this down. Okay. Another one that I like to see is this. You scroll down a little bit and you see this memory workload analysis. So the GPU, much like a CPU, has a low-level cache system, an L1, L2 cache, shared memory. It actually has a bunch of different memory subsystems that don't have analogs on the CPU, right? And when we're looking at things like making sure our memory accesses are contiguous, cache misses, maybe even register spilling and whatnot, we need to have an idea of how we're utilizing each part of that subsystem, and this gives a really nice. You can't tell here because it's a kind of a nice example, but these will kind of light up as red or different colors to show you if you're really stressing this part of the memory subsystem and whatnot, and gives you a nice visual overview. And then finally, again, for the super expert, when you really want to get into the assembly stuff here, we have this source PTX analysis and correlation tool. So what this is going to do is it's actually going to sample while your kernel runs where you are in the code, right? Which line of code you're on. And right, GPUs are massively parallel machines. We have thousands of threads running in flight at the same time. So all of these things are averaged, they're statisticals, they're sampled, right? But it's going to give you an idea of what lines of code we're spending a lot of time in, right? I mean, how much easier can it get than that, right? You see a big red bar on this line of code, you should probably take a look there, right? And further, you can look at the PTX and see what the compiler is actually doing, okay? Nsight compute, pretty similar to what we're doing with Nsight systems, right on the command line. That's what you'd be doing with Polaris, NCU, kernel, report, right? The one thing I do want to mention on this is without that -k option, the Nsight compute will profile every single CUDA kernel you have in your application, which in some cases can take a really, really long time and probably isn't what you intended on first pass, right? If you don't know which kernels to look at, you probably should be in Nsight systems at that point, right? So I highly recommend passing that K flag and putting your kernel names explicitly. Okay, skip over that. I did want to mention the roofline plot, right? So did you folks get some experience with the roofline over this workshop? I think. Okay, so that has been okay. So that we'll talk about that concept in the hands-on a bit later. But roofline gives you a nice visual opportunity to see if your kernel is compute bound versus bandwidth bound, and depending on what the different bandwidth limitations are of your memory subsystem and whatnot. So we'll talk about that a lot later this morning. Okay, so that covers the profiling tools. Again, I hope you can kind of use this as a reference as I upload these slides here shortly. But I do want to talk really, really quickly in a little bit more detail about the correctness checker tools or the other tools as well. So first, CUDA GDB, right? So as I mentioned, very similar to standard GDB, which kind of outside of printf is kind of one of the first go-to debuggers you use, right? Very, very similar, unified CPU and GPU debugging, right? You may have heard NVIDIA is actually coming out with a CPU, Grace, that will be here pretty soon. Built on GDB and uses a lot of the same commands, right? So if you're set breakpoints, all that jazz, no problem. Okay, and then another big one. Anytime I'm starting to run into a bunch of bugs, and I just want to get a bit of a sanity check, we have these compute sanitizer tools. Okay, so these are similar to like valgrind or cache grind. They're tools that will statically analyze your code and look for bugs or look for issues. Right? Look for example, if you're maybe trying to access memory outside of the bounds of an array you allocated, maybe it'll look for race conditions, maybe data that you allocated but you never cleaned up. Right? So this is just something that's really nice to kind of pass your application through. You don't have to think too hard about it, but you get really useful information outside of it. Okay, and then any Visual Studio users here? Okay, we do have some. I have seen more and more programmers in academia actually tending toward Visual Studio, it seems, which is pretty good. I just want to mention, right, we have, if you just go on the Visual Studio Code Marketplace, there's actually an Nsight plugin, and not only do you get all these debugging tools and whatnot, but you actually get really nice like source highlighting and syntax highlighting. So if you are a Visual Studio user, check that out. If you're an Emacs user, they probably have some version of that too, I'm sure. And then as we're finishing out here, one thing I did want to mention is, my job as a solution architect, I spend all day working with developers out in higher ed, academia, national labs that are developing scientific applications, and I help port or optimize code to GPU, right? And it turns out that that's very similar to what we do as an organization with the Open Hackathons group, right? So Open Hackathons, they put these GPU hackathons on. The name recently changed. It was formerly known as GPU hackathons. There was recently one at Argonne maybe a couple of weeks ago. Did anybody join that one by any chance? No, it's definitely something to keep in mind for the future. But these are events where essentially you bring your code, maybe it's all CPU, maybe you've done a little bit of GPU wherever you are, and you assemble a team, you bring your code in, and you sit down with a mentor who they're often from NVIDIA, national labs, other vendors. They'll sit down, they'll work on you with your code, help you port and optimize it on GPU, right? And we have really, really good success out of these events, right? A lot of times people come in, they have code that's really ripe for GPU acceleration, and they don't even know it. I got to tell you, if anyone here is using NumPy, please have a chat with me later this afternoon, because I've seen some really, really good in speed ups out of that. Argonne, like I said, had an event a couple of weeks ago. There's one coming up at Oak Ridge, another one coming up at NERSC, and the applications are still open. If you're curious about these, have any questions about what the event's like, please reach out here, and I'd be happy to help you out. But other than that, I'll go ahead and upload these on the Slack for everybody, and we have some useful links. Right, we have this GTC conference twice a year now, where a lot of the engineers will go through and talk in more detail about some of these developer tools. So really good resources to follow up on. Any questions?
So do any of your performance tools work with MPS?
With MPS, that is a really good question. I can't say I've ever ran one of those through MPS. I would assume so, but I'm not sure.
Okay.
Yeah.
The answer was no.
It was no. Okay.
And so I'm not sure whether it does.
Yeah, I'll have to check because depending on when that answer was taken, right? Because the MPS was changed with Volta and more of a GPU-centric kernel. So yeah, it's a good question. Yeah.
The visual memory analysis chart you showed, are the unified cache hits the L1 cache hit?
Could you say that again?
So in the visual memory analysis chart you showed, are the unified the unified cache hit percentage the L1 cache hit percentage?
Yeah.
So unified is for L1, but you can see the cache hit rate for L1 or L2. They're both printed on there. Yeah. Yep. Good question.
Does NVTX have a performance impact that I should be aware of?
So yeah, NVTX has a very small performance impact, such that it's recommended to disable it for production code. For example, on that one TensorFlow container that I showed on NGC, they are enabled by default on TensorFlow. So if you're submitting that for production, you'd want to disable those. Furthermore, if you've ever used the TensorRT backend, they're enabled by default on that as well.
I have another question.
Of course.
Can I use these tools connecting to a remote machine that I have root access to, or does it have to be local?
Yeah, so I'm not sure if you can SSH in the user interface. So you're talking about from the user interface SSHing to a remote system. We haven't had that capability before. I don't think we have that now. That being said, the typical again is just to use the command line version on the system and then bring it over. It's such a security headache trying to get everything ported through SSH, especially when you need to go to a head node and then jump it further to a compute node to actually do the analysis, right? Yeah. All right, thank you.